Good day everyone. The topic that I will be going to discuss is all about depth first search and breadth first search. Let us go to depth first search. It starts a graph's traversals at an arbitrary vertex by marking it as visited. So let us check the graph here. So here in graph, so it is called a graph. This is called a traversal stack, which the first subscript number indicates the order in which a vertex is visited. Push onto the stack, and second one indicates the order in which it becomes a dead end. And the third is a DFS forest. So let us discuss it with the following examples in the next page. We have also here an algorithm here. So let us discuss it later. Here is the algorithm. But first, we have to analyze first the graph given by its text. Here in our graph, so we have two graphs here, A, D, C, F, E, B, and the second graph is G, H, I, J. We have also here what we call the adjacency matrix representation. So here in the given graph, all we have to do here is, like for example in A, so A has a children here. A has a children, so C, D, and E. All we have to do here is type 1 for C, D, and E. And the remaining here is put a 0. And B, we have two children here, E and F. So we have to write here in E and F, and the remaining here is 0. And same as C, D, E, F, G, H, I, and J. So in J, I leave it blank, so we try to create a simple representation here. So in J, let us look for the graph. In J, we have two children here, G and I. So all we have to do here is, in J, we have to find the G. Here in G, so right here 1, and I, right here 1, and the remaining will put a 0. And that's all for adjacency matrix representation. We have also called here, we have here also an adjacency list representation. So let's find the adjacency list. So in A, we have C, D, and E, C, D, and E children. Next B, we have E and F. In C, we have A, we have D, and we have F. So that is for D, E, F, G, H, I, and so on, and J. Okay, so that is for adjacency list representation. So what we have to do here is to find the stack. Okay, let us write here also the result. So here in stack, we have to follow the alphabetical order in the graph. So we have to we have to pick an A, push it on the stack, visit it, and mark it as visited. So in A vertex, we have C, D, and E vertices, or adjacency unvisited vertices. So we have to follow the alphabetical order. So we have to go to C. So in C, we have to push it on the stack, we visit it, and mark it as visited. So in C, we have two adjacent unvisited vertices, D and F. A is also visited here, so we have to do nothing here. Then we go to D, so that is the possible way. So D, we push it on the stack, we visit it, and mark it as visited. So in D, we have no possible way, so we have to do a backtrack. Okay, so in D, we have to pop it off on the stack. We have to delete it. Okay, and we go back to C. So in C, we have possible way here. So F, there are unvisited vertices. So we push it on the stack, we visit it, and mark it as visited. So in F, there are two possible unvisited vertices, so E and B. So we go to B, we push it on the stack, we visit it, and mark it as visited. So in B, we have unvisited vertices here, the E, so we push it on the stack, we visit it, and mark it as visited. Okay, so here in E, we have no possible way, so we have to pop it off on the stack, and we have to go back to B. So here in B, we have no possible way, then we pop it off on the stack, and we go to F. So here in F, we have no possible way also, and we pop it off on the stack, and we go back to C. Next in C, we have no possible way also, then we pop it off on the stack, and we have to go back in A. So in A, we have no possible way, then we pop it off on the stack, and that's it for first graph. So there is also a second graph here, the G, H, I, and J. So we have to go to G, we push it on the stack, we visit it, and mark it as visited. So in G, we have two possible vertices, which is unvisited vertices. So we go to H, because we have to follow an alphabetical order. So in H, we push H on our stack, we visit it, and mark it as visited. So in H, we go to I, so we push it on the stack, we visit it, and mark it as visited. And in I, we go to J, so we push it on the stack, we visit it, and mark it as visited. Next, in J, we have to go to backtracking. So in J, here, there are no possible ways, so we have to pop it off on the stack, and we go to I. Okay, so in I, we have no possible way also, so we pop it off on the stack, and we go to H. So in H, we have no other way, then we pop it off on the stack, and we go to G. And G also has no other way, so we will pop it off on the stack. Okay, so now the stack is empty, and our DFS is now complete. So then let's go to an algorithm of this graph and the DFS forest. Okay, so this is the algorithm. This is the graph, and this is the answer for our stack. And all you have to do here is to identify the algorithm of its graph. So let's begin. So in algorithm DFSG, so we mark each vertex in V with 0 as a mark of being and visited. So all we have to do here is to mark all the vertices to 0. So let us write 0 here. 0 because they are unvisited vertices. Okay. Next is to count. Okay, so it satisfies that. For each vertex V and V2, if V is marked with 0, then we have to start this DFS algorithm. Okay, so here in count plus 1, mark V with count. So let us go to DFS A or vertex A here. So vertex A, we have to mark it as 1 as it count. So A will become a 1 here. Okay, so you have now A. For each vertex W and V adjacent to V2, then who is adjacent to A now? So C, D, and E. So let's pick C. Okay, so let's pick C. So if W is marked with 0, so it means C. If C is marked with 0, so this condition will satisfy. So we go here. So in this condition, I will call DFS on that vertex. That is, I will call DFS of C, which effectively means I have added C next to A. Okay? Then, so I will call DFS of C, and then I will increment this count plus 1. So it will be going to 2. Okay? And mark V within A count. Okay, so it is now 2. So next, who is adjacent now to C? So C has unvisited vertices, so D and F. So we go to D. Okay, so if D is marked with 0, then we go to a condition which I will call DFSD, which effectively means I have to add D here. Okay, and I will call DFS of D. I will have to increment this count plus 1, so this will go into 3. So in D here, we have also A and C has also been visited, so we have to do a backtracking here. In backtracking, we have to step one at a time. So we go back to C here, because we don't have to go back to A, because D is an ancestor of A, so I have to put here a dash line here. So next in C, I will go to F. Okay, so in C, I will go to F here. Okay, next, for F is marked with 0 here, then I will call DFS of F and increment it plus 1. Okay, so F here will become 4. Okay, so here in F, there are two adjacent unvisited vertices, so B at E, so I will go to B. Okay, so B, if B is marked with 0, then I will call the DFS of B and increment it, so B will become 5 here. Okay, so next, in B, there are which vertex W and V adjacent to V2. So what is the adjacent vertices of B? So B has a adjacent vertices of E, so I have to put here an E. So if E is marked with 0, then I will call the DFS of E. So I will go to count and I will increment and add it plus 1. So E will become 6. So now in E, so in graph, so there are no adjacent unvisited vertices, so we have to backtrack again. We have to go to B. We don't have to go to F because it is his parent, so I have to draw a dash here, dash lines. We don't have to go back to A because it is the A is the ancestors, because E is the ancestors of A, so I have to draw a dash line here. Okay, next we have to go back to B, so there are no adjacent unvisited vertices, so we have to go back to F. So in F, so there are also been visited, so we don't have unvisited vertices. Then we go back to C, so there are no also adjacent unvisited vertices, and we go back to A, and we don't have any possible way. Okay, so that comes from graph 1. Okay, so A, C, D, F, B, E are also marked as visited. Okay, we have a second graph here, the G, H, I, and J. So it's also marked as 0. So we have to go back here in the first statement. So mark each vertex and V, so also we mark it as 0 now. Then for each vertex, V and V though, if V is marked with 0, then we will start a DFS algorithm again. Okay, so count plus 1, mark V with count. So we start in G here. So we start in G here. So we have to increment it plus 1. So I have to write here. So G will become 7. Okay. For each vertex, W and V adjacent to V do. So what is or who is the adjacency for the G? So we have H and we have J. So we have to follow the alphabetical order. So we have to go to H. So in H, if H is marked with 0, Then, in this condition, I will call DFS H. Effectively means I have added H here next to G. So I will call DFS H, and then I will increment the count here. Go back here. I will increment the count. So the count becomes 8 here. So that's it, 8. Next, for each vertex W in V, so in H, who is adjacent to H, we have G, so it has also been visited. So we have also a I here. So if I is marked with 0, then I will call the DFS of I, and then it will increment it. So the count will become 9. So I will put here an I. So I is next to H. Next, what is for H vertex? I and V adjacent to V2. So what is the adjacence for I? So I is adjacence for J. So adjacence for J. So if J is marked with 0, then I will call the condition of DFS of J. So I will call the DFS of J, and then I will increment the count here. I have to add 1, and the count will become 10. I will put here the J. Okay. Next. So in J, so we have no unvisited vertices. So we have to go a backtrack. Okay. So in J, we don't have to go back to G because G is the ancestors of J. So I have to put here a dash line. Okay. So we have to go back to I. So in I, also we have no adjacent vertices. So we have to go back to H. Also the H has no unvisited vertices. So we have to go back to G. And the DFS now is complete. And that's all for DFS.